Hello, I'm Peter Walter, Product Manager and Market Manager for ABB's Low Voltage Drives, located in New Berlin, Wisconsin. Today what I'd like to do is take an opportunity to discuss with you a little bit about our ACS800 Ultra-Low Harmonic Drive. First of all, what is an ultra-low harmonic drive? A low harmonic drive is basically a standard AC drive with a unique front end that allows us to reduce the harmonics imposed on the AC line. Instead of using the typical 6-pulse diode bridge, we're using an active front end and an LCL filter. These two items are contained inside the unit and in combination provide a low harmonic content to the AC line, typically less than 5% regardless of the distribution system. This provides a simple alternative to multi-pulse solutions, which oftentimes use external filter arrangement. The operating principle of the active supply or active input is essentially the same as the inverter section of an AC drive. Just as the inverter section takes the DC bus and creates a near sinusoidal current waveform out to the motor, the active front end provides a near sinusoidal current waveform to the AC line. The only noise that we see, in fact, is the switching frequency or carrier frequency noise, which is why we utilize in the ACS800 an LCL filter. This LCL filter strips out and cleans up that switching frequency noise, providing near pure sinusoidal waveform in terms of current to the AC line. Now that I've told you a little bit about how ABB does it, let me tell you a little bit about the ABB product offering. The ACS800 ULH is available in two varieties, one a wall mount version, the other a freestanding or cabinet version. The wall mount is available in horsepowers from 10 horsepower up through 125 horsepower and voltages of both 230 volt and 500 volt. In the freestanding units, we range from 75 horsepower all the way through 2800 horsepower. These voltages are from 500 volt class and 690 volt class. Both the freestanding and the wall-mounted units are available in NEMA and UL Type 1 enclosures. Additionally, the freestanding units are available in NEMA or UL Type 12 enclosures. As always, we can custom build modules into any type of enclosure so that we can meet any environmental requirements that you may have. Custom configurations typically will utilize circuit breakers, field bus modules, disconnects, bypasses both automatic and manual, and a variety of others. You know the wide-ranging ABB product offering in the ULH, but why this particular product instead of some other? Well, the primary reason for an ultra-low harmonic drive is, as its title states, low harmonics. The ULH drive provides the lowest available harmonic mitigation of all of the different technologies out there. Total current distortion is typically 4 to 4.5% of the nominal rating of the drive. Current distortion does not depend upon the network. And while IEEE 519 calls for these types of measurements at the distribution transformer, we can also provide the lowest level of harmonic distortion at the drive input terminals. It's a simple solution for harmonic mitigation, and being a simple solution requires no additional hardware outside the unit itself. There are no hidden costs, and the package, because it is one complete package shipped from the factory, is factory tested as a final assembly. No external devices required, and as a result, you don't have the additional costs of cabling between transformers and drive. All in all, it provides a very compact, very cost-effective solution. We're always looking for the simplest, most effective solution to our problems. This doesn't differ in harmonic mitigation. It seems as though the effectiveness of the solution always seems to add complexity to the solution. With the ULH, we've broken that mold. We go from 6-pulse to 12-pulse to 18-pulse to ultra-low harmonics, the highest level of harmonic mitigation available, but we've taken a back step all the way down to 6-pulse levels in terms of simplicity of the solution. One other method of harmonic mitigation that I haven't touched on yet, but I think we should take a little bit of a comparison against the ULH, and that's a passive filter. While not a multi-pulse solution, one that is commonly used for harmonic mitigation purposes. Now, there are some downsides to a passive filter. Passive filter solutions require additional filters, so that means going outside the box, if you will. More real estate, more hardware to wire up. Secondly, the level of harmonic mitigation that can be provided is really only in the 6 to 8% range. Leading power factor can also be an issue with a passive filter solution, as will voltage drop because of the filter being placed ahead of the drive. With voltage drop, you may not get full voltage out to the motor. Now, comparing that to the ULH, or ultra-low harmonic drive, we don't require anything external to the cabinet, and harmonic quality is typically 4%. Power factor is going to be unity, power factor of 1 in all distribution systems. We get full motor voltage, and there's no risk for resonance. So as you can see, comparing passive filters against the ULH is the clear winner. I'd like to take a minute right now to compare the multi-pulse solutions to the ULH. The multi-pulse solution requires a dedicated transformer in order to achieve its multi-pulse goal. While the drive itself has lower power losses, the overall efficiency is equivalent to the ULH drive. There's a lower power factor in a multi-pulse solution, while almost unity doesn't quite get there. And the effectiveness of this solution depends upon the line balance or imbalance of the incoming power, as well as the balance of the transformer that's being used. When comparing it to an ultra-low harmonic drive, there's no dedicated transformer, no additional hardware, no additional wiring. The lack of these transformer losses, because there is no transformer, results in an equal overall efficiency to the multi-pulse solution. And the ULH drive has a unity power factor. Regardless of what we have on the incoming line or the distribution system, we have unity power factor at the drive. The power performance is robust, and it doesn't matter what the supply or the transformer variations might be, the ULH drive, through the use of its active front end, can compensate for that. We have created an ultra-low harmonic demo unit which allows us to compare and validate different harmonic mitigation technologies on the same distribution system load. This ULH demo system consists of a ULH drive in its entirety and various different front ends that we can attach to this drive. A standard 6-pulse diode front end, that same diode front end and an input line reactor, an 18-pulse transformer with 2 additional 6-pulse bridges, giving us 18 diodes and the transformer, and ultimately, again, the ULH drive. The additional components are all contained in this lower section here, including the 18-pulse transformer and the additional diodes and reactors. We will be driving a fully loaded motor. The load is being provided by an additional DC drive in here so that we can operate under identical line conditions and identical load conditions. We have a harmonic analyzer with a display output brought up to the front of the demo unit so that we'll be doing actual harmonic analyzation of both current distortion and voltage distortion. We'll have the ability to capture the output of the harmonic analyzer on this computer display, and we'll be able to compare side by side the results of the comparisons between 2 different technologies. Let's begin our demonstration by starting the ULH drive, but we'll be starting it utilizing a 6-pulse input. We'll allow the harmonic analyzer to come up to speed. And what you're seeing right now is a real-time waveform with the current and voltage harmonics being displayed in the upper left-hand corner. You'll note that with a 6-pulse input on this distribution system, we're seeing in excess of 40% current distortion and almost 5% voltage distortion. The waveform that's present is anything but sinusoidal. What I'd like to do now is add an input inductor to the 6-pulse front end. You'll notice that the waveform is getting a bit closer to sinusoidal, but it's not quite there. Our harmonic distortion, though, in terms of current, has dropped to the mid-20s at 26%, and our voltage distortion is just sub 3 volts, and 3% rather, in terms of voltage distortion. Going to take the next step up, going from 6-pulse with inductor to 18 pulse. Now the harmonic analyzer is stabilized, and we've seen in the area of 6% current distortion and about 2.5% voltage distortion. Taking a look at the waveform itself, we are really getting close to a sinusoidal waveform. Let's take one final step and move from the multipulse solution to the ULH. Having brought the ULH into the picture, we now see that our current distortion has dropped to a level below 5%. Right now we're in the mid-4s at about 4.5% distortion, and our voltage distortion is down below 2%. The waveform, as I was indicating earlier, is near sinusoidal. At this point, let's capture a few of these waveforms and examine them side by side using the computer screen. When we had individual displays of these waveforms on the harmonic analyzer, while we could see the level of harmonics, we didn't have the side-by-side comparison that we have now. It's very easy to note from this side-by-side comparison the dramatic improvement that simply adding an inductor to a 6-pulse drive can add to the waveform. Looking at these voltage harmonics, current harmonics, and power factors, it's also easy to see that adding an inductor is a superior form of harmonic mitigation to simply the 6-pulse by itself. On the lower graph, what I'd like to point out are the actual levels of the individual harmonics. These are laid out as 5th, 7th, 11th, 13th, etc. in terms of harmonics. And you'll notice the amplitude of each of these harmonic levels. The 5th harmonic and 7th harmonic on the 6-pulse are dramatically larger than they are when an inductor is also used. We'll see this change even more dramatically when we compare the 6-pulse with inductor to the 18-pulse solution. Taking a few more captures of the operation in 6-pulse with inductor and operation off of the 18-pulse, we again can see the dramatic difference on all levels of harmonic performance. Current distortion has dropped from 26% down to 6%. Our voltage distortion has dropped from 2.7 down a little bit to 2.5. We've had a significant improvement in power factor. Total power factor has increased from 0.97 to 1, near unity power factor in this particular case. And if we examine in the lower graph the individual harmonic levels, we see that the 5th, 7th, and 11th harmonic levels have almost come off the screen. And our final comparison is probably the most important, the comparison between a multipulse solution and the ULH. For our multipulse solution, I've captured an 18-pulse waveform and associated harmonic data, and I'm comparing that to the ULH waveform and harmonic data. On the left, the multipulse solution has provided us with about 6% current distortion and 2.7% voltage distortion. As I mentioned earlier, we are near unity in terms of the power factor. When compared to the ULH, we have 4.2% in terms of current distortion, and we're below 2% on the voltage distortion. Total power factor is at unity. Looking at the graphs to the bottom of the screen, we do see individual harmonic levels, even in the 18-pulse, in the 7th, 11th, 13th harmonics. Moving over to the ULH, these levels are almost imperceptible, even on the graph. Once again, our comparison of all types of technologies has proven that the ULH technology provides the best level of harmonic mitigation, both in current and voltage distortion, while providing a power factor of unity and additional benefits that we'll discuss in a moment. Now that we've